Whenever Netflix recommends a film, Spotify suggests a song, or ChatGPT understands your sentence, it needs a way to measure how similar things are. And surprisingly, one of the simplest ways to do this comes from linear algebra. It's called the dot product. So, how does it actually work? Hi, I'm Oliver, a computer science student and tutor. In this video, we'll build a clear intuition for the dot product, what it means geometrically, how to compute it, and why it shows up in so many different areas. Before we go into how to compute it, we will first start with what does the dot product do. So the dot product is an operation defined between two vectors of the same size. So in our depiction here, we have a vector A and a vector B, both of them living in the R2 space. The dot product operation is simply written as such a dot multiplication between the two vectors. And now what we'll do is we'll project one vector onto the direction of the other. So in our case, we're going to take the vector A and project it onto the direction of the vector B. So how we can think of this is we look at the arrow of our vector A and draw a line down to our vector B. And now, of course, we can write different lines landing in different places, but there is a unique line we can draw so that there is a 90-degree angle between our projection, so this line going down, and the vector B itself. So the projection of the vector A onto the direction of the vector B is this projection here, where we have a right angle here. So it would be exactly this point. This is our projection of the vector A onto the direction of the vector B. And it tells us how much of one vector lies in the direction of the other. So when we ask, how much of a vector A lies in the direction of our vector B, the answer is exactly this projection here. So it would be this vector here, and the length of this tells us exactly how much of the direction of B is in our vector A. Now the dot product takes this idea and scales it by the length of our vector B. So we do not simply get the projected vector, this one here, but it also gets scaled by our vector B. So it gets multiplied by this length here. So it means while the projection of A onto this direction does not depend on the length of B, so it could also be this vector here or this vector here, our scalar product also contains the length of B. So if our vector B has this length or this length, makes a difference in what the dot product gives us as a value. Now let us consider the case where our vector B has the length 1. In that case, this projection here is exactly our dot product, because if we multiply by our length of B, it is just 1, so it's the same value. In this case, we look at two vectors A and B that have a small angle between them. So they have similar directions. In this case, our projection here gives us a large positive value. So we get exactly this length here, which is large. Now let us compare that to the case where both vectors are perpendicular. So there is a right angle between the vector A and B. Projecting our vector A onto the direction of B now gives us the point at the origin of B. Since we know that this is a 90-degree angle and they both have the same origin, we know that this projection lands us exactly here. And what does that mean? That means that A does not have any component in the direction of the vector B. And our dot product would be equal to 0 in this case. Now the last case we'll look at is where our angle is greater than 90 degrees. So when we try to project A to a 90 degree to our direction B, we notice first of all, we need to continue this vector here. So draw a line like this to continue that direction and then project our vector A downwards as we've done before. What you notice now is that this projection runs in the opposite direction of our vector b. So in this case, we would say it going in the negative direction gives us a negative dot product. So we see that when two vectors show in similar directions, we get a large value for the dot product. If they show in opposing directions, then we get a negative value for our dot product. And if they are perpendicular to each other, so they have no overlap of directions, the dot product is 0. So we can think of the dot product as measuring how aligned or how similar two vectors are. I also want to briefly mention that the term dot product is often used interchangeably with scalar product. So what we've been talking about here is considered both the scalar product and the dot product. Now let us get to how to compute the dot product. So first I will start with the geometric perspective of the dot product and show you what its constituents are and how this fits in with what we've seen until now. So the dot product between A and B can be written as the product of three distinct parts. One is the length of the vector A, so this length here times the length of the vector B, so this one here, and lastly, the cosine of the angle between both of these vectors, so this angle here. We see that the dot product between these two vectors is dependent on the angle that is between them. That's what we saw before with there being certain values for certain angles between these vectors, even though we didn't change anything regarding the lengths of the vectors. And this now also makes sense that having a right angle between two vectors causes their dot product to become 0. Since the cosine of 90 degrees, so of a right angle, is 0. So this entire term becomes 0. And we also saw that the dot product is dependent on the lengths. So we had to normalize our vector b in order to get exactly this projection. So what we've been working with here, projecting exactly downward with the 90 degrees, this is actually just part of the dot product. Namely the part that is divided by this length. So it's just the length of A times the cosine of theta. So this is this projection here, this vector here. So in case you just want to know how similar two vectors are in their direction, but you do not care about their lengths, you can divide by both of these lengths and get the cosine. This is what you would calculate. The dot product divided by the product of both lengths. That would give you the cosine of the angle. And from this, you could tell how similar the directions are. So if the outcome is 0, you know that they're perpendicular. If it's positive, they show in similar directions. And if it's negative, they show in opposing directions. And the magnitude, so how large the positive or negative values are, tells us to what degree. A value of 1 on this side would tell us that they show in exactly the same direction. So it would mean that this vector A would also be running in this direction. And if this was -1, it tells us that they're in perfectly opposing directions. So they have an angle of 180 degrees between them. So this gives us a geometric way to understand the dot product. But how do we actually compute this in practice? Since when we have two vectors given to us that are in two-dimensional space, all we know are their x and y coordinates, so both values that make up A and B, but not necessarily their angle. And of course, you could go and compute this angle and then use it in this formula, but there actually is an alternative algebraic definition. And this is the algebraic definition. The dot product of vectors A and B is simply the sum of the products of all its entries. Now what this means is that we multiply the first entry in A, so A1, times the first entry in B, B1, and add this result to the product of A2 and B2. And actually this is equivalent to multiplying the transposed of our vector A times the vector B. So these two are equivalent, for which reason you will frequently see the scalar product, or the dot product, written in this way rather than this one. And this formulation looks different than the geometric definition that we've seen, but it gives us exactly the same result. It is just a computational form of the geometric idea. So implicitly, this calculation tells us something about the angle between the two vectors. It incorporates this information. Let me show a quick example. So say our vector A is the vector 1, 2, and B is the vector 4, 2. So applying this above formula here, we would multiply the first entries and add them to the product of the second entries. So it would be 1 times 4 plus 2 times 2, which is 8. And if we apply the lower formula here, which is 1, 2 times 4, 2, we multiply the first row with the first column of the second component, which gives us exactly this form again. So 1 times 4 plus 2 times 2. So we also get 8. So you see that these two formulations are equivalent. The dot product gives us a measure of similarity between vectors. We know that the output of the dot product relates to the angle between two vectors. And this is exactly what recommender systems like Netflix and Spotify use. They represent users and items such as shows, movies, songs as vectors. So they have some representation in a vector space, usually much higher than R2, so a high-dimensional vector space, that encodes some sort of meaning. So perhaps one direction of the vector tells us how much a song is pop or how much it is rock. And each entry has some meaning, perhaps not understandable to us, but encoded in some way that we can apply the similarity to. So let us look at a simple example. We'll consider these three vectors, and let's say each of these is a song. We have song A, song B, and song C. And our listener enjoys this song A and gives it a like. And now our recommender system has to decide whether it recommends the song B or the song C to our user. Using the scalar product, it can tell that this song C is more similar to the song A than our song B. So it would choose this song C to recommend next. Now, in machine learning, the dot product also finds relevance. It allows models to compare representations using dot products. So the same way that a complex object like a song was encoded into high-dimensional space, this can be done for text or other objects. And with words, for example, it allows to measure how relevant one word is to another word in a sentence, which is what large language models use to learn context. And this mechanism in large language models is called attention. So central to this concept of attention in large language models are dot products. And dot products find further applications in machine learning, and typically, when they appear, you have the ability of replacing them. Since we learned that the dot product relates to similarity, we can technically use other types of similarity measures and replace the dot product. And this finds applications in kernel methods in machine learning. So the idea being finding dot products in our formulas and replacing them with other similarity measures that might fit our data better. So we see that a simple geometric idea, so measuring alignment of vectors, turns out to scale to very high dimensional spaces and allowing applications enabling highly complex models capable of imitating intelligence. If you want to see the dot product in action, watch this video on orthogonality. It builds directly on this idea. And if you're learning linear algebra, you can find the full linear algebra basics playlist here. If you want to learn more about large language models and how they encode context or generate text, you can check out my introduction to it here. If there's a concept you'd like to see next, let me know in the comments. And as always, thanks for watching.